Okay, so if we have a container, basically the container contains HF. So I'll write that right here. Okay, and it also contains HCl. Okay, now if we want to figure out the pH, we got to figure out the H plus concentration. And then obviously we're looking for the fluoride concentration, which is going to come from HF. Okay, so far so good? Okay, yes, this will be up here. So let's take a look at HF. First thing we need to determine is its dissociation. So with this guy right here, is it going to be a strong or weak acid? Yeah, this is a weak one. So if this one is going to go into equilibrium between HF and F minus. Okay, if we take a look at HCl, what kind of acid is this?
Strong.
Strong, very strong. This guy deadlifts 700. Okay, so it breaks down into H plus and Cl minus completely. Okay, so Ka is going to be talking about which acid? Yeah, HF. This is going to be talking about HF because HCl has complete dissociation. It doesn't have equilibrium, so it doesn't have a K value. It just completely dissociates. Okay. All right, so the equation that we're going to be primarily looking at is HF going into equilibrium with H plus and F minus. Okay. So we're going to make an ice table. So I'll give you guys a minute to set up your ice table. If you guys want some extra practice and see if you guys can start filling it out, go ahead. And then we'll go over in about a minute, minute and a half. Okay, so set up your ice table. See if you can start filling it in. Okay, so let's start with HF. So what's the initial concentration of HF? Yeah, 0.2 right here. Okay, now we're gonna go through the rest of them. So if you take a look at H plus, is this value 0 like normal? No, it's not going to be 0 because there is another compound in there that fully dissociates, right? That's going to be HCl. Now, if you take a look at HCl, it's 0.1 molarity. So if it has complete dissociation, that means that we're going to have 0.1 molarity for H plus and 0.1 molarity for Cl minus. Does that make sense? Okay, so that means that inside the solution, there's going to be 0.1 HF already, and there's going to be no F minus. Now, you might be wondering, why does this guy get priority? And it's because it's a strong acid. This guy's going to dissociate completely no matter what. HF is going to be basically determined. The dissociation will be determined based on this compound because this gets priority in terms of dissociation. Okay. Okay, so the change, pretty simple. You're going to lose some HF. You're going to gain some protons. You're going to gain fluoride. And so you're going to get your ice table, 0.2 minus X, and then you'll get 0.1 plus X, and then you'll get X right here. All right, so we're going to take this, and then we're going to set it up with the equilibrium constant, which is 6.8 times 10 to the negative 4. Okay, and then we're going to plug in the two values, 0.1 plus X, then you get X for F, and then 0.2 minus X. All right, now, if you take a look at this equation right here, can we automatically assume the 5% rule? No, unfortunately not. So this one, you would have to do the quadratic. I'm not going to make you do it today for the sake of time. I'll just give you guys the answer. X, but if you do the quadratic correctly, if you want to practice doing it, you can. You should get 0.00133. Okay, that's going to be your value for X. Yeah, so that's X. We just need to find out the fluoride and pH concentration. Now, if you notice, X is equal to the fluoride concentration, right? So this is going to be your first answer. Your fluoride concentration will be this value right here. And then for the pH, you're just going to put in the value right there. You're going to add. So this is going to end up equaling 0.10133. And then if you want to find the pH, all you need to do is negative log of this value right here. and that will give you a pH of 0.994. Okay, so those are your two final answers. If you guys want to, just for your practice, do the quadratic and figure it out, you can, but just be able to identify, you'll have to use the quadratic equation here in order to find F minus like this, and then you find pH like that. Okay, I'll skip it since we've been doing this for so long now. It seems like you guys have a good idea on ice tables. All right, any questions on how we got any of those before we move on? Yes. Because the exponent here is -4. Usually -4 and higher, we have to assume that we can't use the 5% rule. If it's less, then we can. Yeah.
That's your final answer, right?
Yeah, pH. Yeah, because the two things you're looking at are fluoride concentration and pH. Yeah, so fluoride concentration, pH. So far, so good?
C.
Yes. Yeah.
So,
yeah, so we can use 0.1 for HCl because we know that HCl is the one that gets priority in dissociation, right? It has to fully dissociate, whereas HF is going to be affected by the strong acid, right? So HCl is going to dissociate completely regardless of the order you put it in or how much of anything else you have in there. And that's why no matter what, you'll start with 0.1 H+. Because in order for this guy to dissociate, HF to dissociate, it's going to be affected by what's already dissociated, which is HCl. Exactly. Yeah, common ion effect. Yeah. All right. Make sense, guys? Okay, so let's move on to the next section. Now, basically what this concept of the common ion tells us is that if you have a common ion in there, that's going to affect the dissociation of another acid or base or whatever you have in there. So that leads us directly into buffers. Okay, so we're going to be looking at something called buffers. Okay. Unfortunately, this is not the secret to getting buffer, but buffers are a type of compound. It's a special type of compounds that we look at when we're looking at acids and bases. Basically, buffers are chemicals that prevent big changes in pH, okay? So buffers are compounds, if you want to be more specific, they're solutions that contain a weak conjugate acid-base pair. So there's an acid-base pair in there, and that prevents a big change in pH. Okay? And this is important, especially in living things, because you're mostly made of water, and there's stuff dissolved in there. So you're like 80% solution. And so if the pH changes drastically, you die. And so you want to make sure you prevent big changes in pH in your body. You already have built-in buffers in your body. Yeah. Yep. Your cells make different proteins and compounds. Yeah. Human body is pretty amazing.
I'm just gonna picture like the little balls on that come out for when you suck.
Yes. That's what a buffer is. It tries to keep it in that range. All right. So you guys can continue writing that, but quick example of buffers. Buffers are very, very easy because you guys already know conjugate acid-base pairs. Basically, a buffer resists pH because it contains an acid, right? And the acid neutralizes OH ion. So if you get like a base in a solution, the acid is going to neutralize the OH. And then there's also a base in there that neutralizes the H+. Okay, so when you have a buffer, you need both an acid and a base. They're conjugate acid-base pairs. And the key thing is that they don't react with one another. Okay, so because obviously if they react with one another, right, then you don't have that compound in there anymore. So that's why buffers are always going to be a weak acid and base conjugate pair. And you got some examples right here. So again, the conjugates. So this one's going to be your acid, the conjugate base right here. And so these two, when they're together in solution, can act as a buffer. Okay, same thing here. We got NH4 plus and NH3, and their conjugate acid-base pairs. Again, the difference is just one hydrogen, and they can buffer each other out. Yeah.
Wait, so if you added an acid to a solution of those two, it would stay the same thing?
It will change a little bit, but it prevents drastic changes.
Like HCl?
Yes. Because like let's take a look at one of these examples. Okay, so let's say this guy right here, okay? So let's say you had a container with this guy in there, right? And you had HCl. HCl breaks up into H plus and Cl minus. What's going to happen is the acetate, the anion is going to react with this to form more of this, right? So it reacts it, and so since it reacts with H plus, you're not going to increase the because pH is negative log of H plus concentration, right? The concentration of H plus won't increase really quickly because it's going to be consumed by this. And then this weak acid is going to be produced instead. And so it's not going to get acidic really fast. So it basically just slows down the process. Exactly, yeah. They react to make the other one, and then that's going to dissociate to make more of this, and it kind of goes into equilibrium. And it prevents this concentration from skyrocketing. Because if you had...
It would shift.
Yeah, it will shift the pH a little bit, but it'll be very, very, very slow.
Oh.
Yeah, so like if you had an empty solution, and then you just put HCl in there, you just get a bunch of H plus, right? pH spikes up. But if you have a buffer in there, it'll consume this and just go up very slowly. Yeah. Yeah, it's reacting with the hydrogen to prevent the change in H plus. Mhm. Yeah. Mhm.
Why would it be?
It will increase just very slowly because the H plus is being used up. Because pH by definition is you need the more H plus you have, the more the pH goes up, right? So if you reduce the amount of H plus, then the pH won't go up as much. Yeah, so it'll still change, just very little. Okay. Okay, so we're gonna look at 12.54 now, just to make sure you guys understand what a buffer is. I'm going to basically what I did was I put, sorry. 3 different conjugate acid-base pairs, so they're all conjugates of one another. But I want you guys to figure out which one of these will not act as a buffer. Okay, and I want you guys to explain. So based on what you learned, definition of buffers and whatnot, I want you guys to take a look at these conjugate acid-base pairs, figure out which one will not act as a buffer. Okay, so you pick one. The answer is A, B, or C, and they explain why your choice will not act as a buffer. So take about 2 minutes to think about that and write it out. Look at the person next to you, and then we'll go over the answer. Okay, anybody want to bravely offer their yes? Yes, you want to share, or the answer is C? The answer is C. Yes. Just making sure, because you start speaking in Spanish to mess me up. Okay, so the answer is C, because if we take a look at all the acid-base pairs, let's take a look at A. Okay, let's take a look at the acid here. What type of acid is this? This is a weak acid. If you look at the second one, is this weak or strong? Weak. But if you take a look at C, it is strong. Okay, this is why you got to remember these strong acids and bases. Okay, so your explanation is super easy. It's C because it is a strong acid. That's it. Okay. Yeah, and buffers are, by definition, weak acid-base pairs. Now, if you want to talk about how HNO3 completely dissociates, you can do that, which means that NO3 minus is not going to want to react with any added H plus, right? So let's say we had a container with HNO3. Okay, it's going to completely dissociate into H plus and NO3 minus. And this guy right here is going to suck at reacting with H plus. So if I added another acid in there, okay, even though you'll have extra H plus, NO3 will not react with the H plus. And so it won't buffer the solution because this guy sucks at reacting with H plus. I'll go Brendan and then we'll go around. Yeah. Yeah, you could say that. And you can say buffers are weak acid-base pairs.
Can you explain why?
Because it's a weak acid and a weak base.
So the key thing figuring out if it's a buffer or not is knowing if it's weak or strong.
Yeah.
Strong acid.
Strong acid base pairs cannot be buffers. Yeah, no, that has no bearing on it. Okay, so let's move on. Okay, so if you guys want to take a look at a video on how buffers work, you can. It's basically what I just explained to you. The anion's going to react with H plus to reduce pH change. And then there's all this other stuff for the math. If you guys really want to look at it, you can. There's a lot of math involved. Okay. And then this right here, is basically what I just told you. Let's say that H plus is your buffer, or HF is your buffer. This is the regular solution. It's going to go into equilibrium between these two. If you add H plus, you're going to lose some F, right? And then you're going to get some more HF, but you're not going to have a super high, H plus concentration. So it's not going to change the pH that much. And then the other way, if you add a base in there, it's going to increase the F minus and decrease the HF, because the H plus is going to react with water, or react with the OH to make water. Okay. Make sense? Easy peasy. This is basically what we're talking about. I just wanted to show a lot of different ways you can understand it so you get how buffers work. Okay, let's look at 12.55. I'll have you guys try this one on your own. Okay, I'll give you guys 3 minutes to try this out. Basically, you're adding NaOH to a buffer, and this is going to be your acid-base pair for your buffer. This is your buffer, basically. Okay. I want you guys to figure out what happens when NaOH is added to this buffer. Second scenario, what happens when HCl is added to this buffer? And I want you guys to write the chemical equations that represent both of those additions. Okay.
Chemical equation?
Yes.
Like
the formula. Yeah. Okay, so try that out, and then we'll go over it together. Okay, so for the first part, we're adding NaOH. Now, let's take a look at this. NaOH is what type of compound?
Base.
Yeah, it's a base. Okay. Now, since this is a base, which of these two is it going to react with? The acid. Okay, now you guys should be able to identify that this is your acid and this is your base. Okay, because again, this is the one with the H plus, this is the one that gave up the H plus. Okay, so NaOH is going to react with acetic acid. This is vinegar. Okay, because this is your acid. Okay, and let's figure out what it's going to produce. Now, we know that when an acid and base reacts, it creates water and a salt, right? So these two are going to react to create H2O. And this will be the compound, sodium acetate. Okay. Okay, so this is what's going to happen. Yeah.
I didn't like board separate equations, but I didn't like the decomposition.
Oh.
CH3CO and then the forming of H2O and the forming of CH3CO.
Wow, that is extremely extensive. Yeah, as long as you have this equation somewhere, you're good.
Is that better?
This is better. Yeah. It's more concise. Yeah, I mean, this is a pretty open-ended question, though. So if you have something that communicates this, like if you can combine them and get this, that should be fine. Okay, so this is the chemical equation. Okay, this is the chemical equation for the first one. Now, we need to figure out what happens to this reaction. So if NaOH is added, what's going to happen to the concentration of your acid? It's going to go down, which means what's going to happen to the concentration of the base in this situation? Yeah. So if you want to just briefly describe something like the concentration of the acid is going to decrease and the concentration of the base is going to increase. That works. Something like that. You don't necessarily have to. I mean, this kind of implies that pH is going to go down a little. Oh, thank you. Sorry. Oh, wrong way. Yeah. pH goes up. My fault.
Notating concentration as brackets.
Yeah. All right. So that kind of gives you a good idea for what happens in the other one, right? The acid is going to react with the base. Okay. And so this is going to react to form Cl minus. And then it's going to react to produce acetic acid. Okay, and this is gonna tell us that the concentration of the acid is going to increase.
Oh, wait.
Huh? Am I missing what? Okay. Is that messing me up? And this will go up a little. What am I missing? Missing some peace and quiet in my life. I don't know, dude. I could have been anything. I could have been anything.
Well, you didn't like the parts thing.
Could have been a doctor, could have been an engineer, could have been a pro StarCraft player, could have been a McDonald's burger flipper. Oh, so much potential. Missed opportunity. So much potential. Wasted on teaching chemistry. Oh my gosh. Oh,
We don't even understand.
no, you guys are
what we're
fine.
considering.
Like, do I believe you exist? Yeah. That you're gonna succeed?
Yeah.
Some of you.
Okay. Name them right.
Name them right.
No, not this class. I think everybody in this class is gonna succeed.
Really, Robbie?
Yeah. Robbie's gonna be a great, successful person. Yes, I agree. And he's gonna come after you. Watch, Josie. Robbie's gonna be a billionaire. He's gonna buy up your house. He's gonna outsource your job to India. I'm just playing. All right, let's move on. Okay, so we're gonna be talking about how to calculate the pH of a buffer now. So copy down this equation. Yeah, we're gonna go over how to do this. So copy down this equation, and then I'll show you guys how to solve out problems like this.
And this are all the tiny stuff. The small one, the fancy one.
This one?
The no. The
That
white
one?
No, the white. That's the white ornament. That's not cut out. Oh, somebody. Okay, I was like, no way.
Okay.
Wait, maybe there's one. That would be crazy. It's
I think
like
the plastic one. There's,
Oh, okay.
Oh, wait.
There's two.
there's two. I didn't even see that.
I thought it was like really. Yeah.
All right. So let's talk about how to take a look at this now. Hopefully you guys copied down the equation. Now what we're gonna do is we're going to take a look at the problem. So it's asking us what is the pH of a buffer. Okay, that is 0.12 molarity in lactic acid. Okay, so it gives you the formula for lactic acid. You can use either of these. Okay, and 0.1 molarity in sodium lactate, and it gives you the equation right here. And then it gives you the Ka for lactic acid. And you might be looking at this like, what is going on, right? There's
Way too many letters.
I know, so many letters, so many words, so much math. Okay, so the first thing we want to do is we want to determine what type of compounds they are and how they dissociate, okay? So let's start with lactic acid. If lactic acid has a Ka value, what type of acid is it?
Oh, it's not strong.
It's not strong, so it's weak, yeah. It's one or the other. You're either strong or weak.
Or your name.
Yes.
Wait, Robbie.
Dude, Robbie, when you get rich, man, just buy up her house. Buy her house, buy her dog, buy her car. And then in front of you, just destroy those things. And send me the dog.
My dog is me. There's like no.
Well, why are you assuming that I care how much meat it has? Dang. Whoa. Okay. So lactic acid is a weak acid. Now if we take a look at sodium lactate, okay, what type of compound is this? So what type of compound is sodium lactate? So first of all, is this an acid? No. Is it a base? No, it's not. So this is neither. However, if you notice, it doesn't have a Ka value, right? So if there's no Ka value, we can kind of assume that this is going to dissociate completely, right? So if something dissociates completely, it's not an acid or base. Anyone remember the term for this?
This is no wait. Oh, it's
Yeah. It is a strong Electrolyte, yeah. It's the thing that's in Gatorade or whatever. Electrolytes. So yeah, so sodium lactate is a strong electrolyte. Now, if you guys remember, the two rules that you guys needed to remember about solubility is number one, alkali metals, they dissociate completely, right? The guys in the first column. And then the second column is going to be anything with nitrate, dissociates completely, all right? So yeah, we're going way back, pulling information from a long time ago. Okay, so that's kind of what you guys need to know. Okay, so far so good? Everybody good? Okay, so if sodium lactate is a strong electrolyte, that means it dissociates completely, right? Okay, it has dissociates completely. I spelled that wrong. Anyway, it dissociates completely, which means that it has 100% dissociation rate, which means when it breaks up, it's going to release the anion, right? So it's gonna break this. It's gonna break up into Na plus and C3H5O3 minus. Now, if you guys notice, what does the anion have to do with the other compound?
It's a conjugate base.
Yeah, it's a conjugate, or it shares a common ion, right? And so we're gonna be doing an ice table again. I know. In order to figure out the equilibrium concentration. So let's go on. Let's scroll down a little, and we're gonna make our ice table. Okay, the key thing to note is that sodium lactate, if it's 0.1 molarity, what's gonna be the concentration of Na plus that comes out of it?
0.1.
Yeah, 0.1 molarity. And then what's gonna be the concentration of the anion? Yeah, same thing. Because this guy dissociates completely. And again, it's because it is a strong electrolyte. Yes. Where?
Just like two different formulas.
Yeah, it's the same thing. If this tells you that the first one tells you what it looks like, the structure. So CH3 is on one side, CH, and then OH, Q, and then Na at the end. So this tells you what the structure looks like. And then this is basically the condensed one, easier to count. Yeah. Yes, I am. Thank you for checking. I'm sorry. I know. I forgot. Old man, small brain.
You're literally 29.
You're literally the youngest.
Okay. Okay, so yeah, that's gonna be. Dude, I lost my train of thought for a second. Okay, so if we take a look at strong electrolyte, this is gonna tell us the molarity. Okay. Now, we're going to take a look at lactic acid now. So lactic acid's the one where the dissociation matters. So let's write down the formula. It's going to be HC3H5O3. It's going to dissociate. Since it's a weak acid, it goes to equilibrium with H plus and C3H5O3. And if you guys notice, what type of problem is this? So dissociation, ice table problem. It's what did we just learn about?
Buffers.
Yeah, it has to do with buffers, but then buffers have to do with
Acids and bases.
common ion. So the key thing is identifying that there's a common ion here. It's okay. That was a very vaguely worded question.
That was very. That was. Don't do that to us again. Shame on you.
Yeah, if you take a look at it, so it gives you the entire formula. And then so if you take a look at it, there's no real place for the hydrogen to be released. Also, if you take a look at this solution right here, usually carbon compounds like this are not going to be acid or bases, especially if they're bonded to a metal rather than a hydrogen. Yeah.
So lactic acid
C3H6. Oh, you could write it like that, but it separates it like this for you, and it tells you it's an acid, so you know one of the hydrogens are going to come off. Yeah. So yeah, it's a little bit convoluted. Basically, you can make the assumption this isn't an acid or something. Even if this was an acid, it's not going to make a difference because you should be able to tell that this anion is a common ion of this. That's kind of what it's looking for, that you can identify that too. Yeah. Yeah, it's a strong electrolyte. It's not going to release H plus into the solution. No. Yeah, so you need to know those two solubility rules. All alkali metals are going to be strong electrolytes. Anything with NO3 minus nitrate is going to be a strong electrolyte. We talked about that in like unit 4. And I'll bring it up during the review month. Yeah. Okay, so let's start filling in our initial values. So what's the initial value for our lactic acid? 0.12. What's our initial value? Do we know the initial value of H plus? 0, yeah. Okay, and then 0.1. Good. Perfect, guys. Okay, so perfect. You guys are perfect just the way you are. Except that you're not. Okay, except for that you're not. That none of you are. Dang, you going at him today. All right, so I'm going to give you guys about 3 minutes. I want you guys to try out this problem. See if you can fill out the rest of the ice table. I'll let you guys know right now. You can use the 5% rule. So you should not be using a quadratic. Or actually, it's written up here. I'm not being nice. You can. Assume it. I'm going to tell you guys you can use it. But I'm telling you that you can use it. On the test, probably not. Yeah. So for the test, you can use all the conventions that I taught you. You can use the formula. You can use you can look at the exponent. But this time, I'll tell you for the sake of time, 5% rule works. Okay? So assume 5% rule. Okay, guys. So I set up the ice table for you. So you guys should get these values. Now I plugged it into the equilibrium constant equation. Now, since we can assume the 5% rule, we can ignore all the changes that are important. So we can get rid of 0.1 plus x. We can get rid of the change here. And that gives you a very manageable equation to solve. Okay, and then that's going to give you a value of x is equal to 1.7 times 10 to the negative 4. Okay, so now you have the H plus concentration. So pH is very easy to find from here. We can just use the normal formula. Okay, so we can plug in 1.7 times 10 to the negative 4, and that will give you a pH of 3.77. Now, if you wanted to use the equation we just learned, that will also give you the same value. So if you do the pKa plus, but this is going to be a lot of extra work, okay? I'm just going over it so that you have this in your toolkit so that you guys can use it. But if you guys plug in the values from here into here, you should still get the same value.
You should do that.
No, I'm good.
Show us.
pKa is this, or negative log of this. Put the base concentration right here, acid concentration, you're done. Yeah.
So there's no circumstance where like one will work and one won't.
Yeah, they'll all work together. It's a closed system, so it'll work. Yeah.
So why would we ever use that?
I don't know. For example, if I wasn't asking for pH, or if you didn't have certain variables to plug into here.
Okay.
Yeah. All right. You guys comfortable with that? With identifying the stuff? Okay, that's fine.
Make sure the Robbie's you.
Okay, let's move on to the next topic. We're gonna skip a lot of questions, and then we're gonna go on to more stuff about buffers. Okay, so when you are looking at a buffer, the two important characteristics of a buffer are capacity and effective pH range. Okay, capacity. Okay, so make sure you guys jot that down somewhere. Capacity and effective pH range. Okay, so capacity is very simple. It's basically the amount of acid and base that it can neutralize before pH starts changing rapidly. Okay, so how much acid or base can a buffer take before the pH starts going wild? Okay, the range is the pH range, as the name suggests, where the buffer can actually work effectively. Okay, and then there's a bunch of descriptions about that, but that's the two key things that you guys need to know. Okay, buffer capacity is how much, this is quantity, right? So we're talking about concentration, or not concentration, sorry, volume. Okay, so the volume of acid, well, that does depend on concentration. Volume and concentration of acid or base that the buffer can neutralize before it stops working. And then pH range is what range of pH it can actually work effectively. Okay.
How much would it take for our buffers in our bodies?
Depends how big you are.
What if you just drank like straight H?
That'll burn a hole through your stomach before it gets into your bloodstream.
Is that like dependent on how much of the buffer there is, or is it?
Yeah, usually it's gonna depend. Oh, it's gonna depend on two things: how much, like the volume, but it's also gonna depend on the concentration. So, like, if you put like I don't know, like a gallon of 0.001,
Yeah.
right? That's not gonna affect it very much. But if you put like 100 milliliters of like 12 molarity, that's gonna affect it very drastically because it is more concentrated. There's a
So,
lot
like, how
more.
much kind of buffer?
Yeah, and that also depends on how much buffer you have too.
Oh wait, so it's like if, is that why like if you drink too much water, die?
That's because it starts taking